you should be thinking about your presentation topic. So there are some suggestions on the website. I will probably set a deadline, I don't know, maybe roughly 2 weeks from now, when you should probably be ready to tell me what the, yeah, let's set that deadline. I want you to know, and I want to know that you know. No. I want you to tell me what topic you've chosen in 2 weeks. And like I'm not going to be strict about it, but some people need deadlines to do things like this. And if I don't set intermediate deadlines, that's like, okay, this time you should be ready to give a practice presentation to another student. There are people who like on the last day will be like, oh yeah, I need to choose a topic. So, I apologize to those of you who don't need these intermediate deadlines, but I'm trying to not let people slip through the cracks. Okay. Email me your topic. I feel like that's reasonable. All right. Cool. Are there any questions? All right. So, one notion which I've sort of mentioned a few times, and I expect you guys have encountered in some earlier class on ring theory or algebraic geometry, is the notion of dimension. Sort of referenced this a few times, but we haven't had an explicit discussion of it. So, definition, hopefully you've seen some version of this before. If X is a Noetherian topological space, I'm not saying anything about scheme structures here, just a topological space. The dimension of X is the maximum of N, where I have a chain. You always have to be sort of careful to get this right. So I want irreducible closed subsets with proper containments. And I want there to be N plus one of them in this chain. And Phi might be all of X, but I'm not assuming that X is irreducible. So these are all irreducible. But of course, C0 might not be. All right. So as I say, hopefully you've encountered this notion in some context. One where I know you encountered it if you took 446 with me. It's the notion of Kroll dimension of a ring. You'll often see that as dim A or K dim A. That's the dimension in this sense of the topological space spec A. Of course, irreducible closed subsets of X correspond to prime ideals of A. So this is the same as saying, here I have A. C0 corresponds to a prime ideal C0, and C0 being non-empty means that it is prime. Prime ideals are necessarily proper. And this contains a P1, and this contains a P2. to Pn, and I'm reversing the subscripts because by assumption, well, not by assumption, I'm reversing the inclusions because taking the vanishing set of an ideal gives you irreducible closed subsets, but reversing inclusions. Okay. Well, if A is not a Noetherian ring, then there's no guarantee that this is finite. The notion still makes sense. I mean, similarly, I didn't really need to say Noetherian topological space here. This makes sense for any topological space, but most topological spaces that aren't Noetherian are going to be hugely infinite dimensional in this sense. So if I took something like R with the usual topology, of course, it'd be very easy to, well, that's actually tricky because there aren't very many irreducible closed subsets. So this will give you weird results if you stick in topological spaces that aren't something like the underlying topological space of a scheme. Yeah. There are weird Noetherian rings with infinite Kroll dimension. It's true. So yeah, I mean, I haven't said anything about whether this is infinite or finite. I mean, the max of an infinite subset can be infinity, right? Like, whatever. Anyways, cool. So, of course, the context where I'm going to want to apply this is when X is the underlying topological space of a scheme. So just some things to note. If X is a scheme, then let's say theorem. Then what do we have? We have, first of all, the dimension of X is equal to the sup over affine subsets of X of the dimension of that affine subset. Right? The way to think about this is if I have a chain like this, I can look at a point in Z0 and I can look at an affine neighborhood around that guy. And I'll find a chain of the correct length, of irreducible closed subsets of that affine subguy. So actually, all the information about dimensions of schemes is in the Kroll dimensions of rings. You just look at all the affine guys that you're built up out of, and you take the supremum of those. I'll note through the usual sort of affine communication lemma business, it's enough to look at one affine cover. Right. So if I have this situation where I have a ring A, have some Fs that generate A as an ideal, then the Kroll dimension of A is equal to the max. I get to say that because now I'm taking a finite set of the Kroll dimensions of, yeah. Well, the issue isn't contained in, it's intersects with, right? And no, because every point in a scheme is contained in affine open. Well, it doesn't have to be contained in every, right? If my scheme has a given given dimension, there's a particular chain of closed subsets that witnesses that dimension, right? And so there's an affine open, which contains a point of C0. So when I intersect each one of these guys with that affine open, I get non-empty closed subsets of the affine open. And you might correctly object that I haven't checked that I won't get equality with the intersection. But come on, that's not going to happen. They're irreducible. Right. So the point is, if I have an irreducible closed subset and I intersect that with an open, then I'm getting an open inside the irreducible closed subset, right? From the perspective of the closed subset, that's an open and thus dense by the irreducibility. And from the perspective of the open, it's an irreducible closed subset. Okay, great, cool. So there's an even stronger version of this, which is I can get away with only looking at local rings, right? So it's a well-known fact about Kroll dimensions of rings that they're equal to the max of the dimensions of the local rings at different primes. So applying that to each of the U's, I find that the dimension of X is equal to sup of the dimension of this local ring for little x and big X. And again, if I think about how would I witness that, well, I would look at a point in C0 and I would look at its local ring. And each of these CIs would give me a closed subset of that local ring. And then using the irreducibility, I can argue that those are all different. All right. So really, you don't, I'm going to assume that you know at least a bit about Kroll dimension from another class. And this is just showing you, oh, you don't really need to know anything else to understand the dimensions of schemes. So the main thing we'll talk about is how to sort of translate statements from commutative algebra into geometric statements about schemes. So let's do a few of those. One useful thing to keep in mind, remember, if my X isn't irreducible and I can write it as a union of X1 and X2, of course, X1 and X2 might have two different dimensions. And when I ask for the dimension of X, that has to be the max of these two dimensions. So if my scheme isn't irreducible, I have to watch out for kind of weird behavior. So a classic example of this is if I take spec of C adjoint XYZ mod XC YZ, right? So this is going to give me, if I write the closed points, that's a subset of C3, and it's the subset of C3 where either Z is 0 or X and Y are both 0. So it's the Z axis and the XY plane. So obviously, this is kind of a boring example, but it's just kind of the easiest one to write down, where you get two different components with two different dimensions. Yeah. I mean, you could assume that they're closed subschemes, but right, this is purely a property of the topological space, so I don't really need to worry about scheme structures. Yes, I mean, the thing that I would think about a little differently there is, so, right, often schemes over C, they have an associated classical topology, where you think about an affine thing as a subset of C to the n. And in that classical topology, they're usually CW complexes, but like there'll be more complicated CW complexes. They'll have sort of stuff that's lower down. So for example, we talked about an elliptic curve. If I thought about the C points of that as a topological space with the classical topology, I would literally get a torus, right? But when I thought of that as a CW complex, I would have to start adding in stuff that wasn't a subscheme. There's a lot of interesting arithmetic in the fact that like these cycles inside an elliptic curve aren't subschemes. They aren't well defined over the complex numbers, right? They're not even complex submanifolds. So I would emphasize that, in this case, the components are boring, but I could have a projective scheme where I had this guy and then some two-dimensional surface off here where they met, right? And then I wouldn't want to think of this as like one cell in a CW complex. I would want to think about it as a subset. Right, so if you're used to thinking about topology, you'll usually have thought about manifolds, right? And manifolds, well, those sort of correspond to irreducible guys. I mean, even more special than irreducible, the next thing we need to talk about is smooth. That would make you kind of more analogous to a manifold. But, somehow like these components, they can be very complicated on their own. The other thing to be careful about here is the dimension of the topological space corresponds to the complex dimension of this corresponding analytic space. Well, I'm looking at the C point, so I always want to take C dimension. So in the cases where I can think about one of these guys as a complex manifold, it's the complex dimension of that manifold twice the real dimension, right? So this is a one-dimensional scheme, but if I think about its C points as a manifold, they're a two-manifold, but a one-dimensional complex manifold. That's just a sort of correspondence to watch out for, right? I mean, if I think about, for example, if I take P1 or Pn and think about its complex points, this is a manifold that people think about a lot when I give it its classical topology, but it's two n-dimensional. Right, and this has a very famous CW complex structure where I take a 2n cell corresponding to one of the opens we discussed, and then its complement is a Pn minus 1. So then there's a R 2n minus 2, etc. One in each even dimension. But somehow I want to think about these guys as complex manifolds and thus as being n-dimensional, n minus 1 dimensions. And they all have corresponding locally closed subschemes, which really do have dimensions n, n minus 1, n minus 2, etc., the way I defined it. If I were to write this down in sort of a schemey way, I would say, oh, there's a map from AK into CPN, which I'll just write the coordinates. You can think about how to sort of be a little more careful about what this means in terms of schemes, where x1 up through xk maps to, well, I have zeros for a while, and then I have a 1, and then I have my A guys. So if I think only about the C points, every C point of CPN will be in the image of exactly one of these, right? Because some number of coordinates are 0, I take the first non-zero coordinate, I normalize that to 1, and the remaining coordinates tell me what element of AN I'm getting to. So if I look at this for A equals n down to 0. This gives me the CW complex on the complex points in the classical topology. Okay, cool. Oh. All right, so what else do we need to know about dimension? So one very important fact is if I have a finite, or actually more generally integral map, and I hate this name integral map because, as I mentioned before, that doesn't mean that the fibers are integral schemes. It means that the that locally it looks like an integral ring extension. That functions on X are integral over the pullbacks of functions on Y. Then the dimension of X is equal to the dimension of the image of phi. And here I'm taking the closed subscheme corresponding to the image. But if I have a finite map, then that's necessarily closed. Finite maps are always projective, actually. And so I'm not really doing anything by saying closure here. All right, this is a very powerful tool for understanding dimensions because there are a lot of finite maps out there. In particular, these are sort of all algebraic geometry versions of theorems we proved in 446. So let me first say the affine version of this. If X is affine and finite type over a field, okay, and there exists a finite map from X to A and K, where N is the dimension of K. Dimension X. And we had mentioned this point about there are very pathological Noetherian rings which are infinite dimensional, but that won't happen if you're finite type over a field. If you're finite type over a field, you're a quotient of some polynomial ring, and your curl dimension is bounded above by the number of variables in that polynomial ring. I'm just emphasizing, in this case, this dimension is finite. So every affine finite type scheme is pretty close to being affine space, where pretty close is defined by having a finite. It's important, right? If you're used to manifolds, you'll think, oh, well, like there's always a copy of Rn as an open subset of your manifold. That's something that really goes horribly wrong in algebraic geometry. I just want to emphasize this. Like this elliptic curve, it doesn't have an open subset that's isomorphic to A1. That's impossible. You can tell that because their function fields are different. So function field is sort of a powerful invariant of schemes that doesn't really have an equivalent for manifolds. And I'm sorry, Jack, yeah, you had your hand up. Yes. Going up, and I think you just need going up. Sort of the important point here is that if Y is 0 dimensional, then X must be 0 dimensional. Once you've proven that, it's not too hard. All right, so this is sort of maybe I'll just mention in particular, sort of implicit in this theorem is that the dimension of an over any field is n. Note, it doesn't depend what the field here is, right? So this field could be some huge function field, but the n still just depends on how many variables I have in my polynomial ring. One helpful special case of this, right, is if I take a0 of k, that's just spec of k. I have spec of a field, no matter how big and complicated the field is, the scheme always only has one point. So if I think about this dimension in terms of closed subsets, I see that I get 0 here. There's only one non-empty closed subset, so I can't get a longer chain of them where they're not equal. This is also actually the easiest way to show that the dimension of the fiber product of two finite type, so here x and y are both finite type over k, that the dimension of this fiber product is the sum of the dimensions of x and y. The reason being that this fiber product has a finite map to a dim x times a dim y. And so since I know this theorem is true for affine spaces, I can conclude that it's true for finite type over k. Now, I only stated this for affine things. If x isn't affine, well, I'm not guaranteed to have this map, but I am guaranteed to have this map on any affine open set. So in general, if x is finite type over k, there exists a rational map. Which is finite on an open set. And I think maybe I said these words, but I didn't write them down. This is what's called Noether normalization. All right, and there's one final sort of important theorem in here. That sort of you should think of as sort of part of this Noether normalization package, which is if x is finite type over k, and integral, so now I mean integral in the sense of irreducible and reduced, then the dimension of k has a description purely in terms of the function field. So it's the transcendence degree of the function field . over K. So this assumption of finite type over field removes a lot of these weird pathologies that can happen. So for example, Noetherian rings of infinite curl dimension. This requires taking a non-Noetherian ring and doing a really crazy localization of it, where the localization is Noetherian, and you're somehow able to have a bunch of different components which have increasing dimension. So finite type gets rid of this. There's a slightly more general condition called excellent, which I'm definitely not going to try to define, that fixes this. So for example, things which are finite type over Z behave similarly. But I have to be a little bit careful because I have to remember that the dimension of spec Z is 1. So this is a very important observation, that spec Z is a curve in some sense. It's one dimensional. So there's a lot of hay made in number theory about the sort of analogy between Z and more generally the rings of integers of finite extensions of Q and one-dimensional schemes over a field. But you sort of have similar kinds of theorems where basically the dimension is, what these theorems tell you you get after a base change to Q plus 1 because of spec Z being one-dimensional and spec Q being zero-dimensional. All right, are there any questions about this story? So another useful property is codimension. So a sub-scheme should have a codimension inside a bigger scheme. We have to be a tiny bit careful about this. So Vakiel only defines this for subschemes Y and X, such that Y is irreducible. And note, I say subschemes here, but I could just say closed subsets. Right? Again, I'm only using topological properties. I'm not using anything about like which subscheme structure I put on. So the codimension of Y, I could put sub X here, probably often I won't bother to, is equal to the supremum of, well, I take almost that same definition, except now Y is my C0. Let me write this down here. Y equals C0 is a proper subset of C1, proper subset of Cn, which is contained in X, might be all of X, but again, these guys are assumed to be irreducible. And I'm not assuming that X is irreducible. Okay. So the reason I have to be careful about this is if I come back to this example, if I take a point in this component, its codimension is 2. It's contained in a proper one-dimensional subscheme corresponding to some polynomial in X and Y vanishing at that point. And then it's contained inside this irreducible subscheme. This has codimension 2. Whereas if I take this point, the only irreducible subscheme properly containing this guy is the line. And there's nothing bigger. So this guy has codimension 1. All right, that seems about right. Yeah, that would also be codimension 2, right? The sort of the biggest component wins because I can take an irreducible subscheme in here containing this guy, right? I'm allowed to use any irreducible subschemes containing this point. So if Y happens to lie in 2 components, I can choose C1 from either one of those components. All right. Oh, shoot. I meant to say this here, and then I started saying this. Also, I could define definition. So every scheme has a dimension. No matter what, there must be some answer to this. It might be infinity. X has pure dimension k if all components have dimension k. So for example, this guy does not have pure dimension any. It's a 2-dimensional scheme, but it has a component that's 1 dimension. Whereas on the other hand, if I took v of xy in A2, that's not irreducible. It has 2 components, but those 2 components have the same dimension. So this is pure dimension 1. Components does not mean connected components. It means the yeah. Let me say this right, but so a these so maybe check whether I should have said Noetherian here. But probably really the right way to say this is whenever I write X as the union of X1 and X2, X1 and X2 both have to have dimension, at least one of X1 or X. What do I? No. All right, no, that's not good. Yeah, I was hoping to not say Noetherian here, but sure, what the hell. When do we ever think about non-Noetherian schemes? Let's be honest. If I have a Noetherian scheme, then by Noether's theorem, there's a finite number of maximal irreducible closed subsets. Those are the components. So if you want to think about this in terms of rings, I'm thinking about spec A. In A, I have the ideal 0, which might not be prime. Noether's theorem tells me there's a finite number of minimal primes over 0, and the vanishing sets of those are the components. So yeah, for this guy, these are components, right? If I looked in C of xy, mod x times y, right? Then the ideal 0 isn't prime because x times y is 0. So x and y are primes. Those are the unique minimal primes sitting over 0. No, a point in the plane has codimension 2. If I took the plane itself as a closed subset, that would have codimension 0 because there's no irreducible closed subset that properly contains it. Yeah. Mhm. Um, I mean, I think the short answer is sort of you want a notion that behaves well with respect to localization. Right. I want an answer that wouldn't change if I passed to an open subset around my point. Right. And so from the perspective of this point, locally, this guy just doesn't exist. Right. I can pass to an open subset that just throws this guy out. And I'll go. Yeah. Yeah. It's a maximal irreducible subset. Sure. Yeah, the reason I like Noetherian is then there's a theorem that tells me that there are maximal irreducible closed subsets, and there are finitely many of them, and the guy is the union of them, right? Um, I am not sure. Kind of seems like you should, but um, right? I mean, how would you do that for, okay, you would pass to the case of affine schemes, and then you want there to be a minimal prime over zero. So what's the theorem that tells you you always have a minimal prime over zero? Right? So like part of the reason that Noetherian things behave well is you have this theorem that says for any ideal, there's a finite number of minimal primes over that ideal. And there's no reason that should happen in general. All right. So indeed, maybe another answer to AJ's question is there's a nice theorem that tells you about this codimension and its relationship to dimension. Of course, what I would want to say is something like the dimension of X is equal to the dimension of Y plus the codimension of Y. All right, and obviously I have to be a little bit careful about this because we just saw that that won't necessarily happen, right? Here we had a point whose codimension was 1, so we got the dimension plus codimension is 1, and here we got the dimension plus codimension is 2. And that's not shocking, that's just telling you that sort of locally the scheme has dimension 1 here, and locally it has dimension 2 here. But that means we have to make this statement a little more carefully. So this is true. I can erase this question mark if X has pure dimension. Okay. Going to be a little embarrassing because I know there was a theorem I was looking at in here. I just didn't write it down in my notes. Better to actually let me not worry about that. But I only have 5 minutes left, and I have things I want to say. So the sort of final theorem from commutative algebra that it's worth knowing about is, so there's this whole section in Vakil on Kroll's theorems, the most important of which is the principal ideal theorem. So if I have scheme X and F is in the global sections of X, so for example, X could be affine and F could be an element of the ring, but there's nothing special about that case. then I can define the subscheme V of F. Now, this doesn't have to be irreducible, right? We saw here, and in A2, I can take the subscheme V of XY, and it has multiple components. So I can't talk about the codimension of this guy. It might not be irreducible. So I have to say every component of V of F has codimension 1 or 0. Now, it's only going to have codimension 0 if F vanishes on a component. But that's a possibility I should be aware of. So in particular, if F restricted to U is not a 0 divisor, UI not a 0 divisor, for all UI and an affine cover, then all components have codimension 1. And I'll just remind you, we had defined an effective Cartier divisor to be a subscheme that locally looks like this, that on every affine open subset, or sorry, on all the open subsets of a particular affine cover is the 0 set of a non-zero divisor. So there's a generalization of this, which is if Y and X is an effective Cartier divisor, all components are codimensional. Maximal closed subsets. Right, maximal irreducible closed subsets. And when I intersect with open subset, I get a maximal closed subset of that open subset. A maximal irreducible closed subset. So, sorry. Now, what happens if we want to look at the 0 set of more than one thing? Then we can apply this inductively, right? Every time, if we look at V of F1 up through Fn, right? Every time we add on a new thing, I can think about first setting F1 to 0, then F2, then F3. Let's say all components of this guy have codimension less than or equal to n. So again, I might have this property where on the vanishing set of F1, maybe on one of those components, F2 is 0. Well, no, I didn't assume anything about this sequence. So yeah, if on UI for an open cover of a affines one restricted to UI up through, then restricted to UI is regular. That's exactly saying that on the vanishing set of F1, F2 is a non-zero divisor and all its components have codimension 1. On the vanishing set of F1 and F2, F3 is a non-zero divisor. So all of its components, the components of its vanishing set have codimension 1, etc. Then this codimension is exactly n. This is when we would call this subscheme a complete intersection is the most common term. Um, and of course, you can generalize this to say, oh, I have a subscheme where locally I can choose F1 up through Fn that do this, but they don't have to all be the same globally. All right. Ooh, I'm out of time. So more about this, we'll have to wait until next time. Yeah. Yes. Yeah. After passing to an open cup. Right. I mean, you sort of, right, that only makes sense on an affine. Um, so I mean, if I'm on an affine scheme, right, then it's always let me be a little bit careful about, let me just say, oh, there might be some hypotheses that I'm not thinking of. I mean, yeah, it's correct that you are minimal over something with that number of degrees. And I mean, somehow the way to think about this is my subscheme. Well, it's defined by the vanishing of some stuff, right? Um, and basically what I do is I go through here and I think about sort of how the dimension drops. And if the dimension of that component, the guy containing that component, doesn't drop when I have an Fi, I can remove that Fi and my prime will still be minimal over the guys that are left. So I won't get my ideal in the nose, but it will be minimal over. Yeah. No, I mean, even this like a effective Cartier divisor, you have to locally do this. So there's you know, we haven't talked about line bundles yet. So really the right thing I should be using to get effective Cartier divisors is sections of line bundles, but we haven't defined line bundles, so it's sort of bad to say that. But so I can pick an open cover that trivializes the line bundle, and then I can write everything in terms of functions. I see. Okay. Yeah, all components of this vanishing set have codimension less than or equal to n. For this, I mean, this is mostly just a sort of like, in what context does this actually make sense? So, sure. Yeah, nothing much is going to change if I say locally Noetherian instead of Noetherian. So, Only finitely many components. If you only said locally Noetherian, obviously that doesn't have to be the case, right? You can take that, right? What's the sort of thing which is locally Noetherian but not Noetherian? It's an infinite disjoint union of Noetherian schemes, right? And so, you can have anything happen with the dimension if you're willing to take this infinite disjoint union. So yeah, I mean, if you only have, I should, sort of think about this carefully, but I suspect if you have finitely many components and you're locally Noetherian, then you're Noetherian.